Hi all. In our GradStats 2024 lab series, we are looking at t-tests for Lab7. In SPSS, we are going to be running two t-tests, one as an independent samples t-test and the second as a paired samples. So again, a t-test is what we use when we want to compare the average on a continuous outcome between two things, whether it's two occurrences or two groups, or between a sample and a population. We're looking at two for t-test. And the t-test result tells us if the difference between those two things is a significant difference or not. Materials you'll need are linked in the description and include two different data sets we'll be using, plus the lab sheet for SPSS. So grab those things and we will get started. So working with our data sets, the first one we'll be working with is the survey.sav data set from Pallant in the SPSS Survival Guide, and we're going to be running an independent samples t-test in that data set. And our research question would be something like this. Is there a significant difference in the average self-esteem scores between men and women? So those two groups are independent of each other, hence the independent samples t-test. Now, the first thing we want to do when we open a data set, any data set, is go ahead and check it over. Make sure everything came in correctly, that our ID variable is nominal, that we have all the variables we're expecting. And for us, we're going to be looking at total self-esteem and the gender variable in which males are coded as 1 and females are coded as 2. So working with that, one of the first things we want to do is get some descriptives, especially on those variables of interest that will be going into our model. So for categorical, we go to descriptive frequencies. We'll grab the sex to take a look at what do we have here in men and women in this data set. I'm going to paste so that we get our syntax window going and we can run that code. So it looks like we have 185 males that represents 42.1% of the sample and 254 females representing 57.9% of the sample. So good information to go ahead and have, and knowing up front that males are coded as 1 and females are coded as 2. Now we'll also need descriptives for our continuous outcome. Descriptives, and this we want total self-esteem, and we can hit paste and be able to run that one. So just on the surface of it, we know we have 436 respondents who have information on the total self-esteem measure. Even though the total sample was 439, it's because there's some missing here, 3. It went from a minimum of 18 to 40 with an average of 33.5 and a standard deviation of 5.4. So all information you'll need when you're helping your reader understand the nature of your variables of interest. So going forward from there, checking the preliminary assumptions for t-test includes a similar variation between your males and females, that's homogeneity of variance, and also the distribution of total self-esteem across the male group and the female group is a normal distribution. So let's take a look at those real quick. Typically, when we are looking for those univariate normality information, we go to Analyze, Descriptive Statistics, and Explore. And this was from a prior lab we did when we were describing the variables, I think Lab 2. So in Explore, we're going to put the self-esteem in the dependent list. In plots, we want to request a histogram and request the normality plots with tests. And then we do want to make sure in options we have exclude cases listwise. So this is ready to paste. So we're going to get the information about this continuous outcome, total self-esteem. Running that with the run green arrow, we get all of this output information. We see that we have 3 missing cases out of the 436, or out of the 439, 3 are missing, therefore we have a valid 436. You got the mean and standard deviation, the trimmed mean, you have your skewness and kurtosis values, and most notably we have our histogram. And just taking a look at this histogram and seeing, is this continuous variable normally distributed? The answer is pretty much no. This is a pretty strong negative skew going on, which makes sense with our skew at negative 0.8. So we would say this has violated normal distribution for a continuous variable. And even in our Shapiro-Wilk test also confirms that we have a violation of normality here. But also being able to check this across the 2 groups, across the male and female group, no problem. Go into your syntax, just go ahead and copy what you have. I'm using Command or Control C to copy, and then coming down a little bit and pasting it with Control V. And then I'm going to add some words here on the end. I'm going to word by sex. So now I'm telling SPSS that I want this same examination of the continuous variable total self-esteem separated by the sex groups. So let's run this one. So now we have them broken down between. We know how many are missing in each of those groups. We have the mean and standard deviation across both of those groups. The tests of normality are significant for both groups. And we have separate histograms here. The histogram of total self-esteem for males and the histogram for total self-esteem for females. So those are all information that we can use in our write-up, especially since we have a violation of normality here. We're going to continue with our analysis though, and just do our regular model testing and talk about it a little bit more when we get our t-test results. So to run your independent samples t-test, go to Analyze, Compare Means, because that's what a t-test does, is compare the averages on that total self-esteem variable. And we're going to Independent Samples t-test. And here, our test variable is the total self-esteem. So placing that, and then our grouping variable is the gender indicator of sex. In here, we have to define which group is which. So in defined groups is where we let SPSS know what groups we have. And we can also right-click within that grouping variable area and get variable information if we've forgotten who's coded what. So males are coded as 1, females are coded as 2. So just a reminder, and then we can go into this defined groups and make sure it's 1 and 2. Like sometimes we have things coded 0 and 1. For this gender variable, this sex variable, it's 1 and 2. Continuing here, and we're going to paste. Oh, you do want to leave estimate effect sizes checked. So if that's unchecked on yours, make sure it's checked. And hit paste. And now we have our t-test. And label this independent t-test. And running this guy, now we have more information. It gives us the group level statistics, again the mean and standard deviation of total self-esteem in the males group, and the mean and standard deviation of total self-esteem in the females group. So that's just information that we're going to want for the write-up. In our test, here's where we start looking over the information, and especially considering the test for homogeneity of variance assumption. That's going to be this Levene's test for equality of variances. So that's the first place you're going to look in a t-test, is looking at the Levene's test. Were there equal variances across the males and females for this t-test? And the significance value is 0.062. That means it's not a significant test. And again, when we're talking assumption tests, typically a significant test means there is a violation. When we have a non-significant test, there's not a violation. Violation of what? Homogeneity of variance, because that's what we were testing assumption-wise. So because we do not have a violation there, we're going to use our information off this top row. If we did have a significant Levene's test here, we would move down to the second row, and this is the Welch's t-test, which has more correction in it for unequal variances. But we're fine for the top row for this t-test. And it says our t-test is not significant, so this is our significance column for the actual t-test. Our t-test is not significant, and that means there is no significant difference in total self-esteem between males and females, between those two groups. So for our write-up, we're going to need the t-test estimate, the degrees of freedom, the significance value, and the effect size, right? Well, for effect sizes, we look at this down here are independent samples, effect sizes. Cohen's d is typically the one we're using, especially if we have no violations of assumptions, equal variances, everything's pretty cool. Then our point estimate is the effect size estimate here. Cohen's d is 0.16. Now notice that Hedges' correction, which we might consider with all of that violation of the univariate normality, the normal distribution of total self-esteem across our groups, we might want to look at Hedges' correction. But notice that it's the same estimate anyway. So that's going to be our effect size that we report. Now on our lab sheet, if we scroll down towards after our interpretation, which is what we've been talking about so far, you have this block about our guidelines for effect sizes, and this is from Cohen 1988. Cohen's D, small, medium, and large. 0.2 is small. Our Cohen's D was 0.16, and a small effect size is 0.2 according to the Cohen's d cutoffs. So it makes sense that we have a very small effect, like it's less than small, when we're having a non-significant test there. And if you want cutoffs for Hedges, there's also a website here that has a good summary of our Hedges cutoffs. So what does this write-up look like then? Let's make this a little bigger. So our write-up, again, as usual, we let the reader know what type of test was conducted, let the reader know what information, what variables were going into that model. So we had total self-esteem, males and females. And it's a good place to go ahead and kind of scoop in your descriptives there for your mean and standard deviation of total self-esteem for males and for females that we got. A visual inspection of self-esteem indicated a negative skew, both overall and within each gender, which is a violation of normality and was confirmed with a significant Shapiro-Wilks test. Now, in the test itself, results for the test, while males had a slightly higher self-esteem score compared to females, I'm letting the reader know that there's a figure that they can see. The difference was not significant, and then there's my stats line for the t-test. What test was conducted, how many degrees of freedom, the estimate for the test, the p-value for the test, and the Cohen's d effect size. In other words, there were no significant nor practical differences in self-esteem between males and females, right? So that's, in a nutshell, our model testing part of the write-up. You would have already had introducing your reader to the data set and telling the reader about the general descriptives. How many males, how many females? Generally, what's the mean and standard deviation of total self-esteem? So all of that would have already occurred before your model write-up. Now figures, because t-tests have categorical independent variables with a continuous outcome, a good option for figures are box plots. So let's take a look at those. I'm going to show you a simpler way to get to box plots than using the chart builder. So we're still going to go to graphs, and we'll go to legacy dialogues, and here go to box plot. We're going to select simple and make sure summaries of groups of cases is the indicated here. And then going to define, we're going to say our variable is total self-esteem. Our categorical axes will be sex. Now we're going to paste this, which we don't usually paste coming from Chart Builder because it gives us too much syntax to actually work with. But look at the syntax from this simpler approach here. Pretty straightforward, right? Examine variables, total self-esteem by sex, give me a box plot, and that's basically it. So running that, and now we have a nice little box plot here. Now, to use this for a write-up, you have some edits you need to do. Like I would want to open this up and make sure my capitalization on my axes is correct. Like just make it all simple here. I'm going to just take off that because I'll indicate in a title, in a figure title for the write-up, I'll just indicate in the title what this is. I don't need these grid lines, so I'm going to double click the grid lines and put them to transparent right there. Hit apply. What else might I want to do here? It looks good. I'll close this, and now I have a nice pretty figure that I can put into my write-up. So let's see what I did with it here. So the number is bold, the title is italics for APA. There's my nice little box plot and correctly labeled with no grid lines. So that's how we would move from SPSS into our write-up. And all I did in the output is I just right-click and put copy. And then I pasted it right into my write-up. Okay, so that's it for our independent samples test. What we want to look at next is our dependent samples or paired t-test. Our paired samples t-test is used when we have one group of people that we're measuring twice, because t-test is still just two. So on two different occasions. It's also used for matched pairs, but that's not the research question that we are addressing on this one. Our research question: is there a significant change in participants' fear of statistics test scores following participation in an intervention? So we're going to be using a different data set here called experim.sav. Again, it's from the Pallant SPSS Survival Guide. And just like before, the first thing we want to do when bringing in a data set is to confirm that it loaded into SPSS correctly. So I'll go to my file. There we go. Experim.sav, and notice that SPSS is saying this is data set 2. And that's important, especially if you have more than one data set open. You don't want to think that you're running an analysis on one and SPSS is doing that analysis on a different one. So looking through, we can see that the ID variable is incorrectly typed. So we need to turn that to nominal. And we can even say identification number. We got our gender variable, our age variable, and the variables we're looking at when we're saying, is there a difference in fear of statistics scores at the beginning, at time 1, and at time 2. So the two variables we're interested in here are FOST1 and FOST2, and those are both indicated as scale, so we're good there. Now, we would want to gather descriptives on these variables to help give an introduction of the data set to our reader and also describe especially the variables that are going into the model. So again, if I'm working with categorical variables, I would use frequencies, but I'm not working with categorical variables in a paired samples t-test here. I'm looking at the two measures of occurrences, and both of those measures are continuous. So what I'm going to want is descriptives and my FOST1 and FOST2. And I'm holding down the control or command key to select two items that are not right beside each other. I'll check options. That looks good. I can go ahead and get kurtosis and skewness here. And we're good there. I'm going to paste and then run this. Notice it says data set activate data set 2. So it's letting SPSS know which data set it's running this on. And then in my output, there we go. We see that we have 30 in each condition. So very much a designed to be equal conditions here. 30 in each condition. We have skewness and kurtosis values. We have the mean and the standard deviation. And of course we can use Explorer to also get a lot of this information plus our histograms. So let's go to Experim, making sure I'm on the right data set. I'll go to Analyze and Descriptive Statistics and Explorer. Here I want FOST1 and FOST2. Put those over here. In plots, I want the histogram and the normality plots. And it's exclude cases listwise. Pasting and going over to my syntax. Here's my normality check for FOST1 and FOST2. And I'm going to just make sure that SPSS knows I'm using data set 2. So running this, now I have the 30 in the case processing summary, 30 in each condition. I have the descriptives in terms of the mean and standard deviation and anything about skewness and kurtosis. I have the tests for normality, and both of the Shapiro-Wilks test and the Kolmogorov-Smirnov are not significant there. So let's look at these histograms. Okay, it looks all right. It's a little lumpy. And our normal QQ, how well do the points stay on the line? And then also for time 2, FOST2. So I would have thought that was more lumpy, that we'd have a Shapiro-Wilks that was significantly violating, but this is only 30 in each condition, and as we know, Shapiro-Wilks gets more sensitive to sample sizes that are large. So it looks like, according to Shapiro-Wilks, these are not violating normality. It may be that in your write-up, if you feel that this should be mentioned as a potential violation of univariate normality, you can go ahead and say that, but also report that the Shapiro-Wilks was non-significant, right? Now, there's another thing we check in assumptions when we're talking about a paired t-test here, and that is the distribution of the difference between these scores normally distributed? And like, how would we get to that? Well, when we want the difference between something, we just subtract it. So what we need to do is make a new variable called, we'll call it difference. And in the type and label, we can put difference between FOST1 and FOST2. And here, I'm just going to put those things, FOST1 minus FOST2. And I'm going to paste so I can see this in the syntax. And running with our green arrow. So it doesn't show us much in the output. All it says is what you did in your syntax. But if we go to our data set, now we have this new variable called the difference. And if we look at this, we see that the difference was sometimes 2, sometimes 5. Like, it's probably got a whole range to it from let me go sort of ascending from -1 to 10. So we're going to check the normal variation, the normality of this difference variable. And the same way we check univariate normality for any variable. We go to Analyze, Descriptives, and Explore. I'm going to reset this and grab the new one we made, the difference, and put it in the dependent list. And then the same things, checking statistics. In plots, I want histogram and normality plots. And in options, it's exclude cases listwise. I can paste here and check out my syntax. So I'm going to examine the difference variable. There we go. All that same information. It looks like it barely does not violate Shapiro-Wilks. It did violate with Kolmogorov-Smirnov. So getting tight there. And here's what it looks like. To me, that does not look normal at all. So you say what you found in your visual inspection of the histogram, say what the test for normality ended up, and that's what you conveyed to your reader in the write-up regarding assumptions for this difference score here. But now we got all that, we're ready to actually run the paired t-test. We'll go to Analyze, Compare Means, and Paired Samples t-test. And here we want the pair. So we want FOST1 and FOST2. We want this estimate effect sizes to stay on, and you can leave standard deviation of the difference. now it's ready. We're fine with here. Exclude cases analysis by analysis is fine. And we're not using Bootstrap. So we're ready to paste and then come down here and run it. So here we go. Our output for the paired samples t-test, very similar to the independent samples, where we get kind of the overall, what's going on, what's the average in each of those groups, or each of those occurrences at time 1 and at time 2, and the standard deviation for them. We have the test itself, where we're looking across for our significance value. So we have a significant t-test here. So there is a significant difference between time 1 and time 2. And our t value, our degrees of freedom, this is all what we would report in our t-test information here. We have our Cohen's d, and the column you want to look at is point estimate. This standardizer is not what you're after. You're after point estimate. And then we see there's a significant difference, but what does that mean? Was time 1 bigger than time 2 or time 2 bigger than time 1? You find that out here in your first table. We see that at time 1, average fear of statistics scores was 40.2, and at time 2, average fear of statistics scores was 37.5. So we see that the second time point was lower. And are those two significantly different? I mean, we look at it, it's only 3 points, right? But not just looking, look at the test. The t-test is what tells you if this difference is significant or not. So let's take a look at the write-up real quick here. Make this a little bigger. So again, telling the reader what type of test was conducted. You can give them the information on the mean and standard deviation of fear of statistics scores at time 1 and time 2. We can build a figure to show the reader what that looks like. And mentioning about any assumption checking, especially anything that was a violation. The Shapiro-Wilks was non-significant. Results found a significant decrease in fear of statistics scores. So again, pulling in that interpretive statement and also giving the reader our stats line for that t-test all the way through the effect size. Now this is a large effect size. Cohen's d at 0.99, that's pretty large. So even though it might be only 3 points to me, apparently it was a large difference according to the t-test and effect size. Now, what can we do with this figure to build a nice figure here? Well, the best way for a paired samples t-test is to use a bar graph. And we're going to go back to that kind of simple area in Graphs, Legacy Dialogues, and go to Bar. We want the simple bar, but here we want summaries of separate variables right there. And to define that, we're saying the bars represent FOST1 and FOST2. In options, let's go ahead and display the error bars so we get the little confidence intervals for those two. Then we'll continue and then paste. And then see how much syntax that is? That's very little syntax compared to what we get in the chart builder. So this is easy to edit if you wanted a different bar chart. Running that, nice little graph. Still looks pretty tight to me. We can adjust the scale and the tick marks here, and we can remove the grid lines like before. I can double click grid lines and turn them transparent. I can look at the scale and click the scale and then come over here. So you notice how, depending on how you set these, sometimes, and you'll find this in graphics and journals, that if they change these settings, 35, then it makes it look like there's a huge difference there. Whereas if I use 0, now it's not showing, like it doesn't look like a big difference. That's why you have to be careful when you're looking at graphs and looking at what is the difference they're talking about there. So you want to craft your graphic where it's transparent, it's valid, it's not trying to over dramatize a difference that might be overstated. Now we have a significant t-test, we have a significant effect size. I can see like going with the 35 there, but just be careful that you're not overstating the situation, right? So anyway, I'm going to leave it at 0. Close that, and you would want to go ahead and fix your axes labels. So for capitalization and that it makes more sense, it's not just a label that happens to be in SPSS. And I would put a title as well once I got it to Word. Okay, that looks good. And again, all you have to do is right click and copy to get that. And then you can paste it into your write-up. So that's what we have for our lab in t-test and SPSS. And we did a lot here. We ran 2 different types of t-tests. The independent samples when your groups are independent of each other, and the paired samples when you have 2 occurrences of the same person. So take a look at those. Let me know if you have any questions, and I look forward to seeing you at the next lab.